I have come up with some kind of differentiation. I would like to talk about basically, we generally make use of words like analytical treatment and numerical treatment in physics. So, the motivation to bring this video alive is basically to differentiate between these two tools that we have. One tool is called as we generally call it as analytical treatment, and the another tool that we make use of is what we call as numerical treatment. So this is something that we would like to talk about. So I'm telling you that suppose imagine that you are standing on the bank of a river. So you have a river and you are standing on its bank, and you probably you have a stone. You throw a stone, you throw it into the water. Now what happens is the stone that you throw, it follows a beautiful curved path and eventually falls into the river. Now, now imagine that someone asks us, someone asks us that can you predict exactly where that stone will land in the water? And to answer this from a physicist point of view, a physicist immediately faces two possibilities. The first possibility is to derive the mathematical formula that predicts the motion exactly. So this is one part of the solution of the problem. And the second possibility is to ask a computer to calculate the motion of this stone step by step until the stone reaches water. So what we have these two approaches, and these two approaches represent two of the most intellectual tools ever developed in physics. And what are these tools? The one that we call as analytical tool, and the another one we call as numerical tool. So guys, today I want to take you on a journey through these two worlds, the analytical treatment and the numerical treatment. So, I mean, by the end of this video, you should be able to understand basically what analytical tools are. That is basically the target. That's basically the intuition, and you should be able to answer what numerical tools are that we use in physics. Now, I'm going to tell you as well, you'll be able to answer the question that why both of these approaches, both of these tools, the analytical one and the numerical one, are essential. So how modern physics depends on both of these mathematical tools. And at the same time, you should be able to say why future physicists must learn both approaches, the analytical approach as well as the numerical approach. And perhaps most importantly, you'll understand that physics is not merely about finding answers. Physics is about finding the best way to find answers. This is the argument, and this is something that we're going to learn, we're going to understand in a very simplistic approach, so that everybody's able to understand. Now, what I'm going to say is that the human desire is basically to predict the nature. This has all time remained the desire of the humans, and it's happening since ancient times. And since ancient times, human beings have wanted to predict nature, how nature behaves. A farmer, a farmer wanted to know when the rain would fall, when the rain would come down. A sailor wanted to know how winds behave, how we can predict the direction of the wind. And an astronomer wanted to know where these planets would appear in the sky. And a physicist, a physician, I mean, a medical physician wanted to understand how diseases spread. Now, all of these questions have one thing common. You have many questions, but one thing is common in all these questions. And what's that commonality? That commonality is they involve prediction. And physics developed largely because humans wanted reliable predictions, the accurate predictions, precise predictions. To predict anything scientifically, we need tools. And we cannot predict these things without tools. And these tools generally belong to these two broad categories. The categories that I talked about. The one that we call as the analytical tools, and another part that we talk about is what is called as numerical tools. So, we would like to see the essence. We'd like to see the importance of these two mathematical treatments, and we would like to understand at the basic level what these treatments are. Now, to understand this thing, you imagine a traveler standing before a huge mountain. There's a huge mountain in front of a traveler, and one guide hands him a map. In front of him is a big mountain, and there's a guide. He hands him a map, and another guide hands him a GPS device. Now, the map that he has, the map represents analytical method. And the GPS represents numerical method. The map, on one hand, explains the entire landscape that's in front of him. And the GPS tells him exactly where to go at every moment. So there are two things, the map and GPS. Now, both of these things are important. They're both valuable. They're both essential. And at the same time, I would tell you that they serve different purpose. Physics works in the same way. In the similar fashion physics works. as I stood with this example of a map and GPS. And what's here? What kind of tools we have here? And we want to talk about it. What are the analytical tools that we use in physics? This is the argument. Now, I'll tell you at this point of time, analytical tools they actually seek exact relationships. The goal is here, can I express nature through a mathematical formula? A complete mathematical formula. Now take a simple example. Consider a motion, the motion and the gravity. And what physics can do, what physicists can derive here. The physicist can go for the single equation. The single equation that predicts the position at any point of time. That is analytical solution. So you have a problem of a falling object, you obtain and you generalize an equation and you can predict its motion. This is exactly what we call as analytical solution. So I can tell you that the analytical methods in physics, they provide formulas rather than tables of numbers. You have a number of tables. And to take an example for this, for these analytical tools, what are the various examples? The first one should be algebra. And algebra is used to manipulate the equations. So algebra it's an analytical mathematical rule. And then you have calculus, the calculus that was discovered by Isaac Newton. It was developed and it was developed by Isaac Newton. So calculus, what calculus does basically is you're able to study the changes. If you want to study the changes, you can use calculus. And you have differential equations. I mean, there are many physical laws. They are expressed through differential equations. And you have another important analytical tool that is what we call as vector analysis. And this vector analysis is used extensively in mechanics and electromagnetism. Then you have another analytical tool, what we call as Fourier analysis. And this Fourier analysis is used in sound, it's used in waves, and it's used in signal processing. And then to wind up the argument of analytical tools, what we have is tensors, the tensor analysis. And this tensor analysis is important. It is important in it's important in analyzing the nature. Now, I'm going to tell you why analytical tools are beautiful. Why they have this beauty. This is because they reveal the hidden relationships. Exactly. The point here is exactly. Now, to understand, for example, if I take an example, if I apply the force, if the force doubles, what happens to the acceleration? You double the force, what's going to happen to the acceleration? An analytical equation immediately answers this question, that if you double the force, what will happen to the acceleration? And This is insight, basically. Analytical methods do not merely provide us numbers. What they do is they explain the nature of relation between the different physical quantities involved in a correct equation. And if we proceed this idea, what it does basically is it strengthens, uh, it has it has it has its power, but at the same point of time, the analytical treatments, uh, they have their weaknesses as well. They cannot exactly predict everything, and there are weaknesses, and there are strengths, there are exact solutions. I should say, elegant mathematics, and I should say deep understanding. So, analytical treatment has universal applicability. It has certainly it does have weaknesses. I mean, nature is often too complicated because you cannot exactly predict the exact nature of reality. And then comes the real systems. So, what real systems contain? In reality, we have some of the important physical parameters, like we have friction, we have turbulence, we have randomness. Okay, so these are the disturbances that are going to haunt your analytical methods. And there are multiple interactions. The multiple objects are interacting. When such a situation arises, where you have interactions, the analytical solutions, they often become impossible for the problem under consideration. When you have to invoke these disturbances to even discuss the fall of an object under the gravity. So now let's go to another framework. Now, what am I trying to tell is, now you imagine trying to count every leaf in the forest. You have to count all the leaves. For a small tree, you may count exactly the number of leaves. For an entire forest, exact counting becomes impractical. It becomes impossible. And nature often resembles the forest. The nature is like forest. So I can tell you that physics therefore needed another approach. It could not exactly use that analytical approach. That approach became numerical approach, what we call as numerical physics. So, what are numerical tools? This is the argument that we want to learn. As I gave you an example of the forest, in which it's practically impossible to count all the number of leaves the forest carries. So numerical methods, they don't use analytical situations. They use what we call as computation. Instead of finding one exact formula, what they do is they calculate solutions. They calculate solutions, say step, step, and step. So they calculate solutions step by step. It's like, think of climbing a stair. You climb on a stair you reach the top. You don't reach the top in just one jump, but one step at a time. Numerical methods, they work in the similar fashion. They work similarly, the way that stepping on a stair works. Now, let me take an example to get an idea about the numerical approach. To take an example, if I tell you, suppose we have a spacecraft, and this spacecraft experiences gravity, okay, and it experiences solar wind. The gravity is influencing it, the solar wind is influencing it, and there is the presence of the atmospheric drag, and then there is the spin motion of the planet Earth producing magnetic effects. So there are magnetic effects involved. Now, in this problem, the equations become extremely complicated. I mean, instead of solving this problem exactly what a computer does, a computer computes tiny time, it computes the tiny time intervals. It computes 1 millisecond, another millisecond, okay, 10 to the power of minus 3 seconds, then another 10 to the power of minus 3 seconds, then another 10 to the power of minus 3 seconds. And this way, the millions of calculations, after carrying the millions of calculations later, a highly accurate solution emerges. A complicated problem, and you have a solution. What is the important point here is? The important point here is that the numerical solutions are usually approximate solutions. But approximation can be extraordinary. Approximation, I should say, can be extraordinarily accurate. Sometimes the error is less than 1 part in a billion. 1 part in 10 to the power of 9. So we can seek that extraordinarily accurate kind of calculations that we can do using numerical techniques. Now, we have some of the major numerical techniques. And what are these? The first one is the Euler method. This is a numerical method. The simplest numerical method is the Euler method. And then you have Runge-Kutta method. Okay, Euler is a numerical method. Runge-Kutta is a numerical method, and this method is among the most widely used in modern times. And then we have finite difference method. This is another method in numerical approach, and this method is usually used for heat flow, and it's used for wave equations. So we have finite, as I said, finite element method. This one is used in the design of engineering. It's used in engineering design. And then you have what we call Monte Carlo methods. They are also the numerical approach. And what they do is they use random sampling, uh, and this Monte Carlo approach is widely used. It's widely used in nuclear physics, uh, in general, I can say, uh, and not only in nuclear physics, it's also used in particle physics. It's used in finance. You can use the Monte Carlo techniques in finance, and it's used in biology. It has its own implications in biological science. It's used in molecular dynamics that we have in the chemistry world, and basically it's used to simulate atoms and molecules who are making these bonds, the covalent, ionic, and these kinds of bonds. So there again, you can use these numerical methods, what we call as Monte Carlo methods. Now, uh, uh, so this is how we can have an approach of analytical treatment and the numerical methods. Now, imagine a giant uh, a giant mosaic picture. From a distance, if you see this picture from distance, it appears smooth. But when you view this image, when viewed closely, it consists of thousands of tiny tiles. You have a mosaic image. Okay. Now, numerical physics treats nature similarly. A continuous problem is divided into many small pieces. Remember the mosaic giant image. It appears flat, but when you go close, there are millions of small parts, the tiles. The pieces are solved individually. Every piece of that image, then combined into a complete picture. Now let's get a comparison. We had a separate running water for analytical treatment and the numerical treatment. Now let's try to compare the two. Let's try to compare these two approaches directly. So to say, analytical. Okay, so this is analytical and this is numerical. Analytical approach, numerical approach. What you have for analytical, it is exact. For numerical, it's approximate. For analytical, it's purely formula based. You need a formula to predict. And for numerical based, it's purely dependent on computations. It's based on those logic operations. Analytical treatment, it provides the insight of the problem. And the numerical methods, they handle complex problems that cannot be solved analytically. Analytical treatment is often elegant, but the numerical method is often practical. And analytical method it's limited by complexity of the system. And the numerical method is limited by the power, the computational power of the system. So the question may arise, which is better approach? The answer should be neither. That's the wrong question. You cannot say that which of the two methods is a better one. That's basically a wrong question. The better question should be The better question should be, when should each be used? Where should we use the analytical approach, and where should we be using the numerical approach? And being a physicist, I should say that physics requires both. And to end this argument, let's go with the real examples. Let's go with the real examples from the modern physics. Would like to at least feel the elegance, like the examples that we can treat like. Say, for example, if I talk about a black hole, I mean, if I talk about a simple black hole properties, and these simple properties can be derived analytically. There's no problem. You can solve the equations and you can analytically go for its properties. But when we say the collision between the black holes, the collision between the black holes needs numerical simulations. Okay, so this was one example to compare the analytical and the numerical approaches. Now say weather forecasting. For weather forecasting, no exact formula predicts tomorrow's weather everywhere. What is important in weather forecasting is the numerical computation. So numerical computation is essential for weather forecasting. So it plays a very strong role. Otherwise, there is no single equation that can predict the weather for the system that we're talking about. And then we have quantum systems. Say, if I talk about the hydrogen atom, a hydrogen atom can be solved analytically. You can solve it exactly. And then many electron atoms, you have an atom having many electrons, they usually require the numerical approach, the numerical methods. Now, from here, we can move to the galaxies. Suppose we talk about the formation of galaxy. And in a galaxy, what you have the billions of stars. And these billions of stars are interacting. They have the gravitational interaction between them. So you cannot have an exact equation that can predict about this galaxy. Only numerical simulations can handle such complex and complicated problems in astrophysics. So let's talk about the future. I mean, the future of physics. Would it be numerical, analytical? It should be purely quantum mechanical. I don't know, but as long as the information is concerned, the future belongs to physics, who can basically combine both analytical approach as well as the numerical approach. So if you're able to combine the two approaches, then you are in the right direction. So I should tell you that a modern physicist should know. What he should know, first and foremost, he should know mathematics. And then the next step should be the physicist should know programming. And then there should be the physical intuition. And he should also have analytical thinking, because analytical thinking provides the understanding of the problem. And at the same point of time, he or she must have numerical thinking, because numerical thinking provides capability. And together they create a power. They create the scientific power. They should be master in both the approaches. And now I would like to conclude this argument. I would like to stop here, and I should say you that as we conclude today, remember the traveler from the beginning. One guide gave him a map, and another guide gave him a GPS. Do you remember? This was the argument. The map revealed the structure, the structure of the landscape that he was facing. And the GPS guided him through the complexity of reality. So, analytical tools are the map. This is how we can understand it. And the numerical tools are the GPS. Analytical physics tells